We investigate transferring the skills acquired in one task to a set of previously unseen tasks. First, we train the humanoid in the source task with different training methods. Then, we transfer the policies obtained in the source task to various target tasks. Because source task performance is not indicative of the generalization capacity of the algorithm, the transferred policy is not necessarily the best performing policy in the target task. In the short humanoid task, we transfer the policies trained in the source task to a shorter, lighter robot in the target task. The best performing policy trained with Proximal Policy Optimization with clipping parameter 0.1 fails in the short humanoid task. In contrast, the policy trained with strict clipping in the source task can be successfully transferred to a different, shorter and lighter robot. In the tall humanoid task, we transfer the policies trained in the source task to a taller and heavier robot in the target task. Similarly, the best performing policy trained with Proximal Policy Optimization with clipping parameter 0.1 fails in the tall humanoid task. In contrast, the policy trained with SCPPO can be successfully transferred to a taller and heavier robot. In the delivery humanoid task, we transfer the policies trained in the source task to a humanoid that carries a heavy box in the target task. Similarly, the baseline method fails, whereas SCPPO reuses the skills learned in the source task. In the friction target task, we transfer the policies trained in the source environment with a ground friction coefficient of 1 to an environment with a ground friction coefficient of 3.5. Notice that the humanoid sinks to the ground when the ground friction coefficient is increased to 3.5. In gravity tasks, we generate target tasks by increasing or decreasing magnitude of environment's gravity 9.81. When we decrease the magnitude of the target environment's gravity to the gravity of Mars, humanoid falls using the best performing policy trained with PPO with clipping parameter 0.1. In contrast to the baseline PPO, humanoid using the policies trained with SCPPO can perform forward locomotion on Mars. The policy trained with SCPPO is successfully transferred when we increase the magnitude of the target environment's gravity to the 1.5 and 1.75 times Earth's gravity. The humanoid cannot walk and falls immediately in all experiments using the unregularized baseline method. In these experiments, we compare our methods with robust adversarial RL. We first train our robot in the Hopper source task using SCPPO, robust adversarial RL, our methods ACC, and entropy regularized adversarial RL. When we decrease the magnitude of the target environment's gravity to the half of the Earth's gravity, Hopper falls using the best performing policy trained with robust adversarial RL. When we apply early stopping, the hopper can perform forward locomotion. We follow the same procedure in the target environment where the magnitude of the gravity is 1.75 times the Earth's gravity. When we apply early stopping, the hopper can perform forward locomotion. However, hopper falls again using the baseline. Our aim in the morphology experiments is to compare our methods with robust ARL in target tasks where the torso mass of the hopper is changed. In robust ARL, the torso mass range chosen for the experiments is 2.5 and 4.75. Policies trained with SCPPO succeed in the range of 1 and 6. Policies trained with ACC robust ARL succeed in the range of 1 and 7. Finally, policies trained with EACC robust ARL succeed in the range of 1 and 9.